when you got 1 minute left, and then I'll get really annoying once your time's up. So the first talk is going to be solar-wind interactions and the evolution of hydroxyl on the moon.
Thank you. I am very honored to be here and to present an overview of some of the work that we've been doing on the solar wind processing of Lunar Regolith. This particular talk is an overview primarily of the thesis work of Alice D. Simone, who went on to be in the physics department of the University of Nebraska. And then there's a modeling component. It's a very strong modeling component that we've been doing in collaboration with Darby Dyer and Carl Hibbets as part of the Vortices survey node. And I am also very honored to be selected as one of the other new survey nodes. And our survey node down here is called Reveals. And the V part of that is about volatiles, and I'll give you a very, very short statement about what we're going to do in terms of extending this work in the new node. Okay, so I also had the opportunity to give an overview of some of this work 1 year ago, basically 1 year ago today, at the last Exploration Science Forum. And what we showed and talked about is thermal desorption of molecular water on lunar regolith is efficient. This is important. And we know this because we've measured carefully the binding energies of water on a number of lunar regolith samples. And the binding energies range from 0.5 eV, which is ice, water on itself, and out to about 0.8 eV. You might stretch this to 1 eV, but the number of sites that allow you to bind water at that high of a binding energy is extremely low, okay? We also measured, so this is thermal desorption, we've measured the photodesorption cross-section of water and how this leaves when you have a photon interacting with the surface. This is non-thermal. That cross-section is high, 10 to the minus 18, 10 to the minus 19 square centimeters. I'll give more information on this. But if you look at this point and this point, the bottom line is that water does not stick on lunar regolith at temperatures above 190 Kelvin. All right, so water really shouldn't be around on the sunlit part of the moon based on these lab measurements. Now, there were several talks this morning. They were very good, and they gave an overview of the 2.8 to 3 micron band. And we believe that this is a pretty good optical signature of the hydrogen implanted into the regolith and forming hydroxyls, metal OH bonds. And this is a very, very stable bond and a very stable entity. But in the literature, there's this temperature dependence of this, and what I want to show you is that this can be modeled very simply with a very simple first-order OH degradation process. And so the question is, what is this first-order degradation process, and what does it make, right? And so I'll give you the answer, right? It's a first-order process, so it's a hit and scatter, react, and leave event, right? And there are three entities that can easily do this. A hot hydrogen atom, a greater than 5 eV electron. All electrons can do this, but there's probably a threshold in the energy for the electron due to a scattering resonance we know about, and a UV or VUV photon. What do they make when they have this single-order scattering event? They make OH, O atoms, hydrogen molecules, hydrogen atoms, and I'm twisting this up a little bit, Bill. I've always said the solar wind doesn't make water. I'm going to twist this a little bit. The solar wind makes some water, not a whole lot. It's vibrationally excited, but it doesn't survive and it leaves. So it's not making water that sticks. Okay, we'll talk about this a little bit more. And I want to move on and show you this, okay? If you get anything out of this talk, hopefully you get what's sort of in these boxes that sort of illustrates our perspective of what the solar wind process is. This is not a solar wind cycle. It's not a closed loop thing here, okay? This summarizes much of which we believe is going on here, and I think we capture a lot of the physics and chemistry here. And we're going to start out with paying attention that the solar wind implants itself into the regolith. This is well known, and so you can look at the stopping distance, and for the solar wind proton energies, they're stopping at about 50 nanometers, and they create these OH sites. Okay, it's a disrupted lattice site in the mineral, but this is a very stable molecule. Right now, there's a latitude dependence of this because this depends on the flux of the protons, but this implantation profile depends primarily on the energy and it's temperature independent. Now, Bill, we're going to agree on this, but I don't care about hydrogen, okay? So hydrogen comes in and it neutralizes, and it'll skip around and it'll form hydrogen molecules. And both of these diffuse rather readily and they leave. You can get these weakly coupled binding sites with defects, which trap these a little bit, but they're not going to stay around on a time frame that we care about with regard to the optical signature. What we're going to care about is not these, but the hydrogen that implants and makes this OH. This is a stable molecule. It does not diffuse. It's part of the lattice of the silicate. It doesn't diffuse. Okay, so what happens is over time, as time goes on, this OH optical signature builds up within the regolith. That's what's observed. And then there's sort of this weak temperature dependence of this. And so we're wondering, what is that weak temperature dependence? What is the temperature doing? Well, what you have to deal with is there's a diminution of the signal with temperature and latitude. And we think this is a very simple temperature dependence of this first order destruction process, which I already told you is due to H-atom scatterings, electron interactions, or photodestruction, which can make OH and O atoms. And hydrogen I'm going to dismiss, and I'm going to tell you a little bit about the vibrationally excited water that's produced, the OH that's produced, and O atoms. I won't say very much about micrometeorites until the very end. These are rather important. Okay, I'm not going to spend much more time on this slide. This just shows you that the proton comes in, it embeds itself within the penetration depth, and this is the so-called glassy rim. It could embed itself on many particles, so we're looking at the particle interaction, but if I have a porosity, it can go deeper in and have particles beneath this. But the bottom line is what I have is I have an OH build up at the rim here, and this is what we're going to look at, and we're going to say, how is this OH changed over time? Okay, and this is an important slide here, and it's related to Janine's talk, where she takes this lunar regolith and you heat it up and you get water, right? Well, what we've done is you've looked at, and you can look at the optical signature of the OH, this vibrational signature at a couple of microns, 2.83 microns, and you can look at the temperature dependence of this. And this is just an example of you're looking at the temperature dependence of this from fumed silica or fumed silica or fused silica. These are different ways of making the silica, and what it is it's a variation of the defect density of OH, and there are different types of OHs. These are geminal, and there are OH groups that are right next to silicons that are neighbors. There's a different type, which is vicinal, and that's another lattice site away. The point is that both of them, even though the rates are different, nothing really happens above 150 degrees C. So you have to get this stuff pretty hot to generate water by thermal processes. And the moon is not sitting at 200 degrees C or 400 degrees C. This is Celsius. So this thermal process is not active or very inactive on the moon surface, from our opinion. So you have to have another process that does that, or a process that takes you to that temperature on a regular basis. Now I want to give you a little bit more information on the photon-stimulated desorption. We've looked at these real lunar materials here. We have a brush and a basalt sample. And what we've done is, this is an ultra-high vacuum. We hit the surface with a laser, and then we have another laser that skims over the top. And we can measure very carefully the cross-sections and the rates of a removal of all of the water products that I told you about at the beginning, okay? This is an example of one of the machines that we have that allows us to do this. This is equipped with an ion beam, an electron beam, a VUV photon irradiation source, and what you can't see is behind all of this is another laser that allows me to do very sensitive detection of the molecules that leave the surface. This chamber pressure is 10 to the minus 10 torr. The sample can be cooled from 35 Kelvin to 900 Kelvin. And Janine, this is way more sensitive than 1,000 ppm. She knows about this. I'm teasing her a little bit because she actually was my first student, and she did experiments on a machine very similar to this, doing laser detection of molecules off of ice. Okay, so anyway, we have a detection sensitivity which is exquisite. We can detect 1 million molecules in a cubic centimeter. Right, so that's good. So now what we can also do is not only detect them, but the way that we do this is we have our lunar regolith sample. Everybody knows lunar regolith is purple, right? And this is a purple lunar regolith sample. And then we hit it with a 157 nanometer photon, and then right above the surface, as close as you can get, but not scatter off of the surface, you focus another laser. And this is this REMPI detection laser. And I can scan this laser, and I can measure and photoionize the water by this 2+1 ionization scheme. And I can scan the laser, and I can map out the vibrational excitation, the rotational excitation. And there's a trick here. This is an important trick. You got a little puff of molecules that are coming off, and you interrogate them before they diffuse into the chamber, and you can get the number density high enough, and you can vary the delay between the laser that knocks them off and the laser that ionizes them, and you can measure a quantum resolved velocity distribution. That's useful. Okay. Before you do the velocity distribution, you can scan the laser, and you can get the rotational energy and how hot this molecule is. It's a thermometer for the molecule. And you can map out the rotational excitation. And the rotational temperature is about 450 Kelvin, which incidentally turns out to be close to the temperature you need to get any water forming. And you can sit on this line or any number of these lines and then vary the time delay between the laser and measure a velocity distribution. Okay? And these molecules are actually coming off pretty fast. They're at 1,000 meters per second, a kilometer per second. So they're really screaming off of the surface. And we know this, the excited states that are leading to this because we've done a quantum mechanics simulation to predict the velocity, and it's about 1,000 meters. So it's not important for this talk, but we know why this happens. Okay, I got to speed up here. When you do this, what you can do is you do this, measure the velocity distribution, integrate the area, and then measure that as a total irradiation. And then you can extract out an absolute cross-section for this to happen. That's what I said at the beginning, is the cross-section for photodesorption is high. And we know that because we've measured them directly. Now, there's an interesting thing that happens, and there's a subtlety here. The cross-section depends on the coverage. And when I say PSD cross-section, I said photodesorption cross-section, but that's a lie. It's not just photodesorption. It's photodesorption and photodestruction. And we're just interrogating the molecules. The way you do this is you also look very carefully at the number density that are there and the number density that leave. And some of them are leaving as fragments, hydrogen, OH, and atomic oxygen. And some of these are turning out to leave vibrationally excited. Okay, speeding up. One thing that's quite important here is the coverage dependence of this. The removal rate of water from the Mare melt breccia and Mare basalt is about 10 to the minus 18 square centimeters. That's at low coverage. If you move this up here, this is where the removal cross-section for ice is. Now what happens is if you're at low coverage and you sort of remove it all, there is some dissociation that happens, and what you end up doing is you're hydroxylating the surface. Not all the water leaves, some of the hydroxyls stay. Okay, we got to pay attention to that. So in the end, after I've processed the surface, I got a lot of hydroxyls that are sitting there. Okay. Well, if I hit this hydroxyl terminated surface, and we've done this on purpose, we've exposed it with one Langmuir, then we irradiate it for a while, and at a long time, after a while, you see a lot of atomic oxygen coming off. And it's screaming out to like 5,000, 6,000 meters per second. Okay, so there's a significant amount of atomic oxygen that's leaving the surface from photodissociating OH groups, right, which are the terminal sites on every mineral that you're going to be looking at on the moon's surface. Okay. Now, this is the subtlety. I want to show you this, Bill. Okay, so if we look, and we're very interested in OH. So we started to look at OH, and we can see OH there. And there's an OH plus signal, and this is off the Mare basalt, and this is off the melt breccia. So there's a significant amount of OH, but it turns out if you do this velocity resolved mapping, it's coming off at the same time in coincidence with the proton, and we know that this is actually made by vibrationally excited water. Okay, so that's interesting. So there's vibrationally excited water that's being formed. So what happens? We have the photon come in and knocks off O atoms, and then you can sort of make some vibrationally excited water by recombination of these, and there's another O atom. So we take the measurements that we have, and we calculate what the number density is of O atoms above the Goldschmidt crater, and we get 71 per cubic centimeter. That compares favorably with what's been reported many years ago from the Apollo 17 mission. Okay, I'll do 2 more slides and I'm done. Okay, so what we want to do is take this information that we have, and we know this happens, and we're going to say this is our effective loss rate, our first order loss term. We load these up with a proton irradiation, making this hydrogen terminated to hydroxyls, and then we have this first order loss term. We put it in a model. It's a very simple model, and we can qualitatively capture the so-called latitude dependence of the OH signal. And it's paying attention to the fact that at this level here, our OH destruction is matched by the OH production rate, but then there's a subtle change in the flux and the temperature, and then those rates will cause you to have this differential buildup over latitude, which captures qualitatively the observations. So on that note, since the chair, by the way, I'm the session chair, so I can keep going. No. No. So anyway, the conclusions are basically exactly the same as what we said before. We've added more information. There's a lot of vibrationally excited water coming off, a lot of atomic oxygen, a lot of OH. This should be seen by LADI. And micrometeorites will play a large role here. Because what I didn't say is that when you do the modeling, it doesn't give you a 5 eV barrier. The barrier we get out kinetically is 1 EV, which you won't ever get thermally unless you have an impact event. And so I'm absolutely certain that what was really going on is a lot of the proton implantation, but a big part of the water formation is probably a micrometeorite collision. And I'll leave this up for Bill, because these are the activation energies we have, and they're useful, but that's just for water. It's not for anything else.